We are going to start the post-lunch session, keynote lectures. So these keynote lectures will be moderated by Professor Manchanda. Professor Manchanda is one of the pioneer in the X-ray astronomy group at TIFR. Has worked on the balloon-borne X-ray and gamma ray experiments in 1960s and 70s and early space-based X-ray payloads during 80s and 90s. He was the program manager of LAXPC during the year of 2011 and 2012. He was a part of the development of the LAXPC and calibration team. So I welcome Professor Manchanda to moderate this session.
After a sumptuous lunch, I think before sleep catches you all, I can go through two talks. Before I call the keynote speaker, I wish to thank the organizers to invite me here and participate in 10-year celebration. In fact, 3 weeks ago, I had a surprise mail. Can I join this celebration? I didn't know about it. So, as you all know, quest for AstroSat started in '96. So from that day onward, I was involved till I retired in 2012. And after that, I have been outside the AstroSat loop. So this surprise email was very pleasant. So now you heard from Pandian sir that, and Koteshwara also said that AstroSat in its final avatar was a multi-wavelength. So it had a different type of instrument sitting on the same deck. And in layman's word, they didn't like each other. So with so many each instruments having constraints, and then the proposals coming from different scientists to observe at different times, so all mix and match had to be done by the operation team. So for our first keynote speaker is Leo Jackson John, who is going to tell us how did they manage to keep this family together and for the last 10 years, and they could do AstroSat mission operation and various challenges they face.
So, very good afternoon to all. I'll be covering the mission operations and the challenges. So, first of all, let me congratulate and compliment all the teams who have been involved in this successful mission and the completion of 10 years, and it's still going on successfully. So, when we are gathered here again, there is a team at ISRO even now tracking and doing the monitoring and control and providing the science data. So, let me congratulate all the operations team, specifically ISRO, and then teams from mission, subsystems, payload teams, PIs, and all those who are involved in this mission. So, our responsibility was to manage the mission immediately after the launch. That is, I'll cover like this way. I'll touch upon the highlights first, and then the configuration, and then the performance, and then I'll touch upon the orbit, and then challenges, and then the statistics of so far about the observations. So coming to the highlights, as we all know, 28 September 2015 we had launched and completed 10 years. So observations were open for Indian as well as international astronomy community. So far we are completed 55,800 orbits so far completed, and 1,300 plus distinct sources the spacecraft has been pointed to for observe the celestial sources, and 1 performance verification phase, 8 guaranteed observation, and 13 announcement of opportunity cycles completed so far, and 35 terabytes of science data downloaded so far, and 16,50,000 commands uploaded so far, an average of 450 commands per day. So coming to the source selection criteria, how the source is selected based on the science merit and clearing the geometric and spacecraft constraints. I will not go in detail. As you all know that to select a source for observation, it has to meet both geometric as well as spacecraft constraints. So once everything is fine, is verified, the spacecraft is inertially oriented to the source with the roll axis pointed. The roll axis where all the payload view axis is there, is pointed, meeting all the constraints. So this is the overall operations workflow. So from proposal to the product generation. So basically the users at POCs and other users they put their proposals through a software called APPS, AstroSat Proposal Processing System, which is hosted in our Science Data Center. And all the proposals are there in the database. And those proposals are reviewed by two committees called ATAC and ATC. That is Time Allocation Committee and AstroSat Technical Committee. They review for the geometric as well merit of the source as well as the spacecraft constraints. And once it is through, the sources details will pass to the command sequence generator, we call CSG. So there, with the help of the orbit events also, they are translated into commands, and those commands are uplinked to the station. So the ground station, if you see, the one dedicated station, that is Bengaluru 4, was established exclusively for AstroSat having both capabilities in S-band as well as X-band. So normally what we do is the telemetry and telecommand we are doing with the S-band, and the payload download, that is science data download, we are doing in X-band. So once the commands are obtained to the satellite and satellite is oriented to the sources, science data is stored, and once that data is stored, when it comes in the visibility of the station, the data is downloaded. That data goes to the Science Data Center for processing, archival and dissemination, and goes to the payload operation centers, and they do the higher level of processing and put back the data again back to the Science Data Center. So anytime our Science Data Center holds all the data, archives all the data, and so far till from mission live till now all the data is available there in the Science Data Center. So this is how it goes on as a daily basis as an automated process. And for that, if you see here, we have a ground software called Schemax, which does the monitoring and the commanding operation. So this is done in 24/7 operations. So normally we have some 12 to 13 contacts per day for this satellite, and each of the contacts our spacecraft controller has to monitor and then command to the spacecraft for the operations in the subsequent day. So this is how the payloads are scheduled now. The operation sequence planning based on the priority, as we told, with a constraint check. And early morning we heard that there is a onboard algorithm called sun avoidance maneuver. Basically, the important thing is whenever you orient that satellite from one source to another source, during the transition, no time we should see the sun. Basically, because the instruments are very sensitive and they have to avoid the sun while transiting from one source to another. So there is a special algorithm designed on board which takes care of this one. So then other things are, whenever you operate some payloads, which are very, very sensitive, they are operating at a very high voltage from 800 to almost 5 kilovolt, 800 volts to 5 kilovolt. That is the voltage range we are operating those instruments. So these instruments, whenever they are transiting in the South Atlantic anomaly, so we have to make it high voltage, you have to bring it down, and then when it exits that region, you have to make the high voltage up. So this process happens every day, every orbit. So for that, on ground, we predict those timings when it enters and exits those regions, and those times we are uplinking those commands to bring it up and bring it down, the voltages. So this goes on every day. Similarly, once the satellite is in contact with the station, we need to download all the data which is available in the onboard recorder. So we use the phased array antenna on board. So there are two antennas, because since the satellite is held inertially, which phase will see the Earth or the ground station is not known. So we have two antennas on both opposite sides. So whichever favorable, we use that antenna to download the data. Now again the star sensor availability. Here we know that the satellite, once inertially oriented to some source, it has to be very stable to make the measurements. Otherwise, if the attitude is not stable, pointing is not stable, whatever science data you collected is not useful. So to hold that, to give the stability, we are having updates from our star sensor, so that, and we have to hold that inertially, and you should see that there is not drifting too much. So with the gyros and the star sensors and with the reaction wheels, the pointing is held to the specification whatever needed. So coming to the command sequence generator, it generates the command sequence using the final plan created by scheduler. So there is a scheduler running with all the events, and they are all translated into commands which are understandable by the onboard. So that is going via the ground station now. So what happens is it considers the onboard sequence related requirements, SSR management and X-band term. Here important thing is, as we know that the onboard recorder is again has, we cannot have an infinite memory, so that is limited. We can hold the data for maximum 4 orbits. So you should ensure that within that 4 orbits you are downloading the data and see that it is ready for the next recording. Apart from that, if any one of the contacts in the dump, you have any some errors or something, we have to redump the data so that you don't lose the science data. So this process is happening continuously. So coming to the spacecraft configuration, I just want to tell one thing. I'm not going to individual. What we have seen is the configuration what was set initially after the launch, it is holding, except for one of few of the elements. Otherwise, the configuration is intact and the redundancies are there. So what I have marked here is in yellow is one observation with one of the reaction wheels. So we were in the 4RW mode, that is 4 reaction wheel mode for the control. Now we have gone to the 3 reaction mode. That is one change happened, and accordingly the momentum speeds are changed for the wheels. Otherwise, all these configurations are held even now also it is holding. So coming to the payload also, there are some changes in some of the detectors, some changes are made. Otherwise, all payloads are on and then we are going through. So safety logic also some changes we have made, and otherwise it is going on smoothly. So here the subsystem wise all are performing well, and only thing is except that I told the reaction wheel, otherwise all are working well. Coming to the performance wise, if you see this battery, you know that every orbit it charges and discharges. Now 55,000 plus orbits we have gone through. The battery has undergone that many cycles of charge and discharge and still working fine. So the depth of discharge, whatever was there, 17 to 18%, that is still maintained. And the voltages, we are maintaining between 37 to 41 volts, that's also going nicely. The temperature is also maintained very nicely between 13 to 19 degree. So that way, all the power systems wise, everything is fine. Coming to sensors, our star sensor, gyros, and solar panel sensor, magnetometer, pressure sensors, temperature sensors, all are working fine. So coming to the AOCS performance, it is holding to that spec whatever is needed using the star sensor, gyros and wheels. And coming to the RC system, as there is a requirement that no thruster firing should be there in this mission because it may contaminate the instruments, we were avoiding. But however, we had to do certain firings because of the collision avoidance with the debris. So 3 times we encountered during this mission last 10 years, it has come very close to a debris and we have to move out the AstroSat. So that way 3 times we had to do the maneuver. And the fuel balance, we had some 42 kg now, spent around 11 kg, but right now we have 31 kg of fuel also is available in the satellite. So as such, we are not planning any orbit corrections. We are allowing it to decay. Otherwise, there is no problem with this because the payloads, what we are seeing is the celestial source. So that doesn't matter. We are not doing any correction. And the temperature sensor wise, all are fine. And the auto heaters are also enabled. Out of 235, 121 heaters are enabled and they are taking care of the thermal system. So coming to the telemetry telecommand system, everything is fine. Our telemetry monitoring as well as telecommand, everything is fine. Redundancy is available now. Even baseband handling, so the recorder and the SPS, that is GPS onboard we have, that is also working fine. Sometimes we see some hang up kind of thing, but we reset and it becomes normal. So that way everything is fine. So these are the things we do regularly for our spacecraft. First is, even though you orient to the satellite, satellite to that inertial source, there is some drift whenever there is an update gap from the star sensor. So we need to maintain that drift. So that for that we do the gyro drift compensation within to maintain the error between plus or minus 0.05 degree error per hour. So that to maintain that, we need to do frequent corrections on the spacecraft. Similarly, the onboard time drift, we have to maintain plus or minus 100 milliseconds per day. That also is being done. Similarly, when the pitch which is oriented towards the panel, when it is crossing 0.5 error drift, that also we are correcting it now. And apart from that, every day we are uplinking commands to the satellite for making the instruments to go to low voltage at the entry of the SAA and high voltage at the exit of the SAA. And plus, you have to program whenever the station visibility is there for the download of the onboard data. So these things are going on in a routine way. So approximately 450 commands per day we are uplinking. So this is how the orbit has changed now. Initially we were at, when it was launched, it was 639 by 656 apogee and perigee, and then 6-degree inclination. Now it has changed to 622 by 634. So you are seeing here the orbit plotted here. We are allowing for a natural decay only. These two places where we had safe mode occurrence for the satellite, so that some firing has happened. Otherwise, but there is a slope in this. Why? Because the decay is depending upon the solar activity. So that was slightly higher during the last 2 years, 2023 to 2025. The decay was slightly higher. So that way it shows very high. Otherwise, around 50 meters per month it decays. So this is how that apogee and then perigee variation is happening, and this inclination there is no change. So coming to this data acquisition and processing, we have Bengaluru 4 station exclusively for this AstroSat, and whenever we have for any maintenance issues, we are going with backup of Bengaluru 1 station, and then the data collected is sent to ISSDC, processed, and then given to the POCs, payload operation centers, and once the higher level processing happens, it comes back to the ISSDC for archival. Okay. Then this is a statistic just to show that how many stations in the initial phase and now how many passes they have supported for telemetry, telecommanding and ranging, and then playback operations. So what are the challenges in the satellite? If you see now, regularly maintaining that attitude pointing and timing drift with continuous ground estimation and command uplink. So that we need to keep doing regularly so that the data is useful. Then ensuring the safety of the sensitive payloads. And we know here that the payloads are very sensitive, operate in very high voltage, some 800 to, I was telling you, 5000 volts. When they enter in that SAA, no time it should be in the high voltage mode. So that way, those commands are being uplinked from ground. We should ensure that it is always that event happens, okay, and it is safe for the instruments. Then now, recently what we are seeing is the number of sources we are not able to accomplish as it was earlier with the 4RW mode. So 2024 onwards, we are just number of sources are reduced because of this 3RW mode. Otherwise, we are doing the operations normally. There is no problem. So this is the statistics now for the 1300 plus sources what you have done. The prime sources, the sources with the UVIT as the prime instrument is gone for 59%, and the lag space is 20%, SXT is 16%, then comes CZT 3%, and SSM 2%. These are all with the sources with prime as prime instruments configured. Otherwise also, whenever UVIT is there, data is collected for all other instruments also. So coming to the user database, so far the registered users are 3,238 users. In that, Indian users are 2,115, non-Indian users are 1,123. So the number of countries which use this data is 61. So this is how the goes. First, our India, we have 2115, so followed by United States 254, Italy, and it goes on. So this is what we wanted to present today. Thank you.
As you know, AstroSat was launched in September 2015, and I think X-ray payload started working from October. And I would like to, with your permission, read a message from Shikantan. Some of you may know him. He was my guru. He wrote me a very few line note from November 11th, in which he says, I am sure you must be happy that your untiring effort on AstroSat has started yielding results. Unfortunately, this is what his style of telling me. It is 10 years too late. Of course, in astronomy, there is always the unexpected to turn up. Let us hope some new results come. How is your health? Keep busy, and so on and so forth, advice to me. You see, after coming here, I learned 500 papers have been published, 50 PhDs have done. So definitely, AstroSat has yielded a lot of results. But as Srinivasan said, what is the impact it has made? Because this thought also came to me when Shikant wrote me this note. Because when AstroSat was launched, 24 X-ray satellites had preceded it. 11 satellites were still in operation. So the question was, what will be AstroSat known for in future? So that is what we are going to hear from our next speaker, Dipankar. And he doesn't need much introduction. He started at Jadavpur University, did his PhD Institute of Science, then at RRI, then Ayuka. And he has been running data center completely for a complete AstroSat. And all you people have interacted with him. Just on a side note, if things had gone at that time in my way, he would have done that from TFR, but which he did from Ayuka. Welcome, Dipankar.
Thank you very much, Professor Manchanda, for that generous introduction. And you have given me a task which I'm probably not going to be able to fulfill, but we'll see. We have heard this a few times today, in some of the statistics at least, that we have about more than 550 scientific refereed publications by now, more than 1,000 authors, about more than 7,500 citations. And in addition, rapid circulars and notices have exceeded almost 600 now. I am not going to review this. You have the next 3 days for this. So what I would like to do is to just give you a flavor and glimpse of a few selected classes of observations which sort of represent a whole set of areas which are being pursued with AstroSat. So, as you know, AstroSat is built to have simultaneous coverage of a large waveband in this electromagnetic spectrum going from radio to gamma rays. I have indicated the AstroSat waveband. As you can see that that's actually a pretty large waveband. And there are these multiple instruments written at the bottom which cover this set of wavelengths, starting from UVIT at the right edge to the CZTI at the left edge over here. So what do we see? What we see in these bands typically are hot gases. Hot gas in the UV, even hotter gas in X-rays, and the hottest of gases in hot X-rays. And there are sources which are not even describable by a temperature, so we call them non-thermal sources. So they also emit in these bands. And we have these different instruments observing this together. Some of them appear at all wavelengths, some of them don't. So what does AstroSat do well? It looks at the hot and energetic universe, and we have been chasing hot gases and energetic radiation all through the universe over the last 10 years. Starting with stars. Hot gas in stars, the hottest of stars are the young, massive stellar population. And once we are able to trace the location and the distribution of this young, massive stellar population, we can reveal the history of star formation in the region that we can observe, particularly nearby universe. Here are two examples. On the left is spiral arms in a galaxy lit up in ultraviolet stars, which are all the young new stars forming over there, so we know what are the formation locations. On the right, you have this jellyfish galaxy, and you have stars forming outside the galaxy. And this has been revealed by these AstroSat far ultraviolet observations. So as the galaxy moves through the intergalactic medium, gas is being stripped, and in the trails, you have stars forming. So history of star formation is one area where AstroSat has been making a lot of observations. Clusters of stars is another big area. A lot of clusters have been observed, and you will hear more about it in the scientific sessions. Interesting things about clusters is that they harbor some unusual types of stars. In some cases, some variables, and you see some stars like blue stragglers, which are formed due to binary activity. And what AstroSat is able to do do is to find faint but very hot white dwarf companions to these blue stars. And they show up in far ultraviolet. In optical, you don't see them at all. You don't know these companions exist. Going from stars to diffuse medium, hot interstellar gas is either heated by radiation from very hot stars, like a white dwarf illuminating its surroundings and heating up the gas and creating spectacular planetary nebulae. One of the very interesting findings from AstroSat is this faint glow in far ultraviolet coming from hydrogen molecular fluorescence. Professor Commissioner Rao is here in the audience. Let's see his observation. And you can also do very fine imaging of far ultraviolet gas. This is a small part of the Cygnus loop supernova remnant, where you can see all these detailed structures in far ultraviolet. And simultaneously, you can take a spectrum with the soft X-ray telescope, and you can find the elements which are glowing in this region. Going outside the galaxy, going far away, AstroSat also has been instrumental in finding some of the most interesting types of galaxies called Lyman leaker galaxies, galaxies from which Lyman continuum photons leak out and ionize the intergalactic medium. How the intergalactic medium got ionized is a question that people have been grappling with for a while. And these are some of the sources which are responsible. Kanak Saha is in the audience. He discovered this galaxy which is emitting Lyman continuum photons. And here's a Hubble Space Telescope picture of the same. And so now several such galaxies have been identified from these very deep ultraviolet observations of certain specific fields. You will hear more about it from Kanak as we go along. As we move to even hotter gases, we move to X-rays. Accretion flow around compact objects are the places to find even hotter gases. And these compact objects are neutron stars and black holes. And this flow, as matter goes from the companion star down onto the compact object, the flow is unsteady and the emission is variable. And as the matter approaches the compact object, they get hotter and the variability gets faster. So if you take the most energetic photons, the hottest part of the gas, and observe fast X-ray variability, then you're probing regions very, very close to the compact objects. And this is something AstroSat is very well built to do. And, the study of fast X-ray timing of accreting compact objects have helped us measure masses and spins of black holes, measure mass, radius, magnetic fields of neutron stars, and various other properties of the accretion flow itself. For example, this is an example of variable X-ray emission observed from one black hole binary, GRS 915 plus 105. Yadav referred to it in his talk, and this is some of his observations. And there is also observation of the same object using the sky monitor. So scanning sky monitor is also able to observe intensity variation like this using its own detectors. A particular kind of variability which has been of great interest by many, many people observing with AstroSat is quasi-periodic oscillations. So if you take those variability in time, do a Fourier transform, we get a power spectrum, and peaks like this in the power spectrum indicate quasi-periodic oscillations. And these correspond to specific vibration or oscillation frequencies of the accretion flow, and they are related to the local gravity as well as the mass flow rate. And this can help us measure masses and spins of accreting black holes. They reveal the thermal state of accreting gas. Using these and simultaneous spectroscopy, we can find reflection, reverberation, Compton scattering in this material, and the evolution of hot corona around the accreting object, and the evolution and production of jets out of this hot gas. So all of this can be tracked by looking at the quasi-periodic oscillations, their spectral properties, and their change with time. Neutron stars exhibit various types of phenomena. Pulsations, for example, some neutron stars rotate quite rapidly, and using X-ray observations, we can find the rotation period. So you can measure the spin. This is one such measurement using sky monitor data, centrous X-ray pulsations. Then we can measure the spectra. And one of the interesting things about spectra of neutron stars is that you can find these cyclotron scattering features which allow us to measure the magnetic field on the surface. And these things do not remain constant. They vary, and they can vary secularly, and we can find the evolution of both the spin and the magnetic field of these objects over time. If the magnetic field is small, then such neutron stars can exhibit X-ray bursts, thermonuclear X-ray bursts from the surface. And AstroSat has observed many interesting properties of these X-ray bursts, including X-ray bursts going to the highest of energies like 30 kilo-electron-volt, which has not been observed before. So you can characterize the spectrum well, and if you characterize the spectrum of a burst well, that can lead to the inferring of the mass and the radius of the neutron star, which in turn tells us about the state of matter at extreme density that exists inside such objects. Black holes at the other extreme reside at centers of galaxies, and if they are fed, you have active galaxies. A very significant amount of active galaxy observations have been carried out with AstroSat, looking at the central black hole powered emission, and in some cases, the ultraviolet measurements have revealed the extent of the accretion disk which exists around the black hole. And in X-rays, the flux variability, just like the smaller mass, stellar mass black holes, flux variability of around these black holes has also revealed the masses contained in the central black holes of some of these active galactic nuclei. Going to non-thermal emission, the most prolific location is pulsar magnetospheres. One of the interesting things that AstroSat managed to do is to find the polarization of the emission above 100 kilo-electron-volt for the first time. So polarization of hard X-ray emission was measured from the crab, and the result was that the polarization vectors through the entire pulse stay almost close to the spin axis. And this can only happen if the emission at these wavelengths is coming relatively far away from the central neutron star in the outer magnetosphere called the wind zone. And we were able to place where the emission zone is of the emission that we are seeing through AstroSat in these wavelengths. Then the hottest gases and a mixture of both thermal and non-thermal emission, there are no better place to find them other than in gamma ray bursts. The gamma ray bursts occur a few times a day, because we can see gamma ray bursts anywhere in the universe. And AstroSat has been a prolific detector of gamma ray bursts. As of 2 days ago, the total number of GRBs detected with AstroSat was 745. And they signify birth events of black holes. Of these gamma ray bursts that AstroSat detected, AstroSat was also able to carry out polarimetry of over 20 GRBs, detecting at least in 5 cases. And simultaneous spectroscopy and polarimetry of gamma ray bursts are helping to understand the origin of this gamma ray burst emission. details of how the strong emission from gamma ray bursts originate still does remain a mystery to some extent, but observations like this do help in pin down some of the mechanisms. I'll show you one such example with AstroSat. Here is a gamma ray burst of 25th of March, 2016. The burst itself had 2 episodes of emission, separated by about 40 seconds. And we did have competent scattered photons in the CZT detector, coincident with both these episodes. And using that, one could measure the polarization. And we found that the first episode had very low polarization. You only had a lower limit. And the second episode had a detectable and reasonably high polarization. If you look at the spectrum simultaneously, the spectrum of this part was dominated by a black body, and the spectrum of this part was a polar. And that tells us that here we have a thermally dominated first peak and a non-thermally dominated second peak. And so things like that can be done with observations like this. Time is short, so I will wind up just with a few concluding remarks. AstroSat has been and is a very versatile observatory, and it has been used for numerous different science programs over the past 10 years. A strong user community has been built. They are ready for future major space astronomy missions as well. And data collected, every piece of data we collect, has multiple science usage. So even if the data has been used for some purpose in the beginning, the same data can be used for other things. So research with archival data of AstroSat will keep continuing. It is producing result already at a very high rate, and will keep producing science for many, many years to come. And this data archive is also an invaluable source for education. And all of you who are involved in education in any institution or other, I would urge you to take a look at it. And this has great potential to bring space astronomy to the classroom, which I have been trying in my small way, and I'm sure you will find it very interesting. Thank you very much. The question is about what observations can still be done, or what should be done, or I think we should now move. That's my personal opinion. I mean, this has, I don't say this as the chair of the science working group, because then we have to discuss this in the science working group. But my personal opinion is that we should now concentrate more on, take a few target areas, spend long time on very few specifically chosen problems. That is what is going to yield the kind of science which nobody else is going to be able to do. So I have some ideas, but this is not the place to discuss it.
I feel the society now should concentrate on studying the transients which appear right time. In fact, every second day you see what of a transient. Maxi is doing very well. I don't see any observation or role of AstroSat because we don't observe it. So I strongly urge that all the new transients, where we make new discoveries about black hole and bigger stars, we should concentrate. Even if you are having a long observation, ULT, we should break it, and we should do it.
Yeah, thank you. I think that's also a very important suggestion, to follow up transients that occur. We have had a little bit of difficulty to get on transients very quickly after they occur, but any transient which has a relatively long time span, we should be able to do so. Yeah. Yeah.
In principle, X-ray should go as quickly as possible, but then other detectors will not allow certain angles. So constraints might be there.
Yeah. So within the constraints, to the extent we should, we should.
Okay, let's thank.
Thank you very much.